Okay, so, yeah, we essentially just derived that one there. Right? So that's where it comes from. Okay, so we now have a wave equation, and we know that the Schrodinger equation is a wave function, which is essentially the reason we did all this extra effort. Right? So the Schrodinger wave equation is going to be starting out similarly. We're going to start out with our classic wave equation, and then we're going to show that that's what it has to look like. Right? So we're about to do another fun derivation, finding the time-independent Schrodinger equation, which is, this is what you're going to find in the books. So where the heck does that come from? Okay, so again, we're going to be starting from here, right? And we're going to use that separation of variables again, where u is equal to capital X of x, capital T of t, multiplied together. So we're still going to use u of x, t being equal x of x, t of t. We've already figured out what t of t is, right? It's essentially a cosine function. It was cosine plus a, it's cosine plus something, but this part here is a constant, right? So we could just say it's a cosine of some function of x, right? Or, well, not x because it's time. So what we're going to do, we're going to say, we're going to let u of t be equal cosine of omega t. And this is where our omega is our angular speed. And for our x value, we're going to have x of x. We're going to just take it from a nice x and turn it into psi. Okay, so we previously had, we plugged the top one into here. We had before d squared x of x, t of t, dx squared equaling 1 over d squared x of x, d t t squared. Yeah. Okay, so plugging in our, let's see, yeah, plugging in our x's, our new t values and our new x values. This gets us cosine omega t d squared psi of x dx squared is equal to 1 over v squared psi of x. Now, we're taking the second derivative of cosine. The first derivative gets us sine, and then the second derivative gets us negative cosine. You guys okay with that? Yeah. So, second derivative of cosine is the negative cosine of omega t. We can say that this then is equal, oh, sorry, it would be, close, the second derivative would be, negative of omega squared cosine omega t. Okay. So we can call this, we're gonna bring the negative and the, omega squared out. So this would be omega, negative omega squared over v squared psi of x cosine of omega t. We have cosine omega t on the left, cosine omega t on the right. They cancel out. This part here cancels out that part there. Right? You divide both sides by cosine omega t, they cancel out. So simplifying this or rewriting it, that's d squared psi of x dx squared is equal to minus omega squared v psi of x. If we move this to the other side, right, subtract that, or I guess add it to both sides, we get d squared psi of x dx squared plus omega squared v squared psi of x is equal to 0. What? No.
Why are you adding?
I just move this to the other side. There's a minus there.
So it's not associated with omega, it's just like minus omega squared over.
Oh, it's negative this side. It's not negative omega squared.
Okay.
Could write it out as minus there. Yeah, so I add that to both sides, moves it over to the left. Okay, now W we said was the angular speed. So, or sorry, omega is the angular speed. Angular speed is equal to 2 pi over the frequency. And the velocity, so trying to make these different, times your wavelength is equal to your frequency. If we were working with the speed of light, right, remember the speed of light is equal to
Maybe it's v equals mn.
well, we'll come back to it. Okay, so plugging those in for here. So this would be V is equal frequency over wavelength. Plugging that into there, we get second derivative psi of x dx squared plus we get this. We got frequency squared here, frequency squared there. So we got a numerator and denominator, they're going to cancel each other out. Okay, so we're going to call this equation 1. Okay. That. So, purpose of the Schrodinger equation is to figure out the energy of a particular state. So, it'd be helpful to look at the energy, right? Remember that the total energy is equal to the energy that is kinetic plus the energy that is our potential. Now, a lot of places, if you look on internet sources, they end up using capital T for kinetic energy and a capital V for potential. It's what you're going to find a lot of places, right? So I'm just trying to make you aware of where those capital T's are. I think the reason that capital T gets used for kinetic energy is temperature is a measure of the kinetic energy, but it gets used a lot. Okay, so our energy kinetic equation is 1/2 mv squared. Momentum is mass times velocity. So we could write out our kinetic energy as being equal to our momentum squared over 2 times the mass. So that means our total energy total would be equal to momentum squared over 2m plus, and then so that your notes are now consistent with what you're going to find in the book, I'm going to use V. But V is our potential energy. Okay, so potential energy is V. I'm doing that because that's what you're going to see in the book, and I wanted your notes to be consistent with those. So if we solve this for our momentum, right, essentially moving the V to the other side and then multiplying both sides by 2m, and then taking the square root, we get our momentum is equal to the square root of 2m times energy total minus our potential energy. Okay. Now, from de Broglie, the wavelength is equal to Planck's constant over our momentum. So we can take this, plug it in to get an expression for our wavelength. So that would be Planck's constant divided by, I'm going to use a 2m E total minus V of x. Then I'm going to do the 1/2 power. Same thing as the square root. Okay, so now we have an expression for the wavelength. I'm going to plug that, this is equation 2. I'm going to plug equation 2 into equation 1 for that wavelength right down there. All right, so I'm plugging equation 2 into here. That gets me second derivative of psi dx squared plus 2 pi divided divided by this whole thing squared. So that would be h squared, I'll write it out, 2m e total minus e of x, 1/2, that whole thing squared. Okay, so because this 2m et minus vx thing is on the bottom of the denominator, we can move it up to the numerator. Sorry, this is psi of x. So this would be equal second derivative of psi dx squared plus 2 pi drop. I think I dropped squaring. Oh. Yeah, this was omega squared here. Omega is 2 pi v, so I forgot to square the 2 and the pi. So 2 squared, pi squared. So this here would be 4 pi squared. 4 pi squared. There we go. That looks better. Over h squared times 2 m e total minus v of x psi of x. Okay, we can simplify this part here. If you recall that h hat is equal to h over 2 pi, right? Or sorry, h bar, not h hat. So this would be h bar squared. What's right there?
The inverse.
Well, yes, sorry. The inverse of h bar squared. Yes. Okay.
Are you missing the x by the lambda? Or it's like d squared, the kind of pitchfork and then x?
Oh, yeah.
What's the pitchfork called?
Psi, capital psi. Okay. So, we can move this to the other side, giving us d squared psi, second derivative, psi dx squared is equal to 2m over h bar negative e total v of x psi of x. I'm going to move this here, the 2m, back to the other side. So that gives me h bar squared over minus h bar over 2m d psi of x squared dx squared equal a total psi of x minus v of x psi is moving this potential energy over to the left-hand side. So that gives us negative h bar squared over 2m d squared psi of x dx squared plus v of x psi of x to equal e psi of x. Okay. If you look at this, there we go. If you look at this, there are no t's, right? There's no time anywhere in here, right? There's not a t. The size might look like t's, but it's not actually a t. So this is time independent. So this is the time independent. Schrodinger, C-H-R-O dot dot. Equation. Oh, yeah. When you're looking in the textbook, they don't put a T there for total energy. It's E as in E, that's the total energy. A lot of times I like to put the T there, but in the book, you're gonna see it in that form.
What happened to the 4 pi squared?
So 4 pi squared became h bar. So h bar is equal to h over 2 pi. We have 4 pi squared over h squared, and so that is h, 1 over h bar squared. So the 4 pi and the h are right there. It's a weird, it's a constant that gets used a whole heck of a lot in PChem. Because there's a lot of conditions in which we have the Planck's constant and then a 2 pi. And so it got used so often that they just made a related variable out of it.
And when would you use this one? When would you use this?
We're going to use it a whole heck of a lot. This is like, when you would use this semester. We're about to use it a whole bunch.
Because the last one was just basically draw.
That's just a wave, an equation for how a wave moves with time, kind of like a guitar string. This is how, using that wave equation and the understanding that for the Schrodinger equation, it's expressing, or it's coming up with a way of expressing energy of a particle or a state using wave functions.
So with that, I can find the energy of a.
With that, you can find a whole lot of stuff.
But right now, it's equals to E, right? That
Yeah,
is the
E
total.
is the energy. We're gonna see how, this is actually crazy powerful. It looks simple-ish.
It doesn't really look simple.
Well, okay.
That's
It's, you know, something you can write out in a couple seconds, but this actually is like everything. It's pretty amazing stuff. Okay, so if you have all of this stuff here, so I can turn the slides back on. Okay. So that's where that equation comes from, right, is that derivation. Okay. So the fact that it is a wave equation, we can't actually reverse that energy has to be the wave equation. The first postulate of quantum mechanics is that described by a wave equation. There's no actual proof that it is, we just assume that it is described by a wave equation and do what we just did to show what that equation looks like. Similarly, in classical physics, force is mass, mass over distance, mass over distance, yes. Okay, so, now that we have our equation, we're gonna look at translational motion. We're finally getting into chemistry. Well, this was all chemistry, but we're actually gonna start talking about molecules. Well, sort of. Eventually we're gonna get into molecules. So we're gonna look at a bunch of different systems. We're gonna look at a one-dimensional particle, called a one-dimensional particle in a box. Really, it's a particle on a string, because if you're on one dimensions, if you're restricting motion to one dimension, it's on the string. You're going to be doing a particle on a surface for the homework. So that would be a particle in a two-dimensional, quote, box. And we're going to, in class, do a three-dimensional box. So essentially, if you pay attention to this is the more complicated case. So we're going to do the easy case, the really hard case, and then by yourselves, you're going to do the intermediate. Okay? If you follow what we're doing for this one, that one's essentially similar, it's just less variables. Okay?
On the exam where being asked for 2D, or what
The homework.
on the exam, what could appear on the exams?
Stuff.
Any of them?
You can do particle in a sphere, particle in a ring. Once you understand the process, you can apply it to a whole bunch of different functions. The reason why you'd want to do like particle on a ring is it's the classic way of describing a benzene ring. Right, so the particle is the electron moving around the ring, and that's how you can actually come very close to figuring out the first excited state, the HOMO-LUMO gap for benzene. From that, yeah. Okay, so first, before we restrict the particle, we're going to let it fly free. Right? So particle moving, not inside of a box. So, well, you have this both in your notes and on the previous slide. So, free moving particle, if it's free, then there's no potential energy, right? There's no forces acting on it, which is what free means. So, we're going to use the function that we had before, right? We had minus, this is starting to give up the ghost, over 2m d squared psi. And I'm going to drop the of x because it's a function of x. And it gets kind of repetitive writing the x a whole bunch of times. Plus v of x, psi of x, that's equal to e psi. All right, for this system here, v is equal to 0. Right, we're talking about a free particle. If this is equal to 0, then that whole part goes away.
Negative h bar squared.
Your h bar squared. Yes. Okay, so we're going to use a wave equation, and similar to what we were doing when we were talking about the classic wave, we're going to use e to the e to the ax. Okay, so that, we're gonna use that as our wave equation. That was the same place that we were dealing with when we were talking about x, right? In our, the string moving up and down, we had a step where we got to something that looks like that, right? Constant times e raised to I something x, plus b e to the negative I something x, right? So we had a similar thing in that previous derivation that we did for classical mechanics.
What's that key for?
We're gonna get there. So the k is essentially some constant time, so it's kind of like our a value that we had before, but now we're doing a new one, so we're using a new variable. Okay. So plugging this in for our equation here, right, to see what this ends up being equal to. So we're going to take the second derivative of this, and hopefully that should equal a constant times this. That constant will be e. Right, so the left-hand side should give us back this function times a constant, and that constant will be e. Doing this gives us back the function plus e is some constant value. So to figure out the energy value, we need to take the second derivative of this. So taking, we're going to do h bar squared negative 2m, taking the second derivative of that, d of a e I kx plus b e minus I kx squared dx squared. Okay, taking, we can break this up into two derivatives, right? And that would give us minus h bar squared over 2m times what we would get from the derivatives. That should be a I k squared e to the I kx plus b to the minus I k squared e to the minus I kx. This part here, the square of the negative of I kx, we could write that as the, well, if you square the negative, negative times the negative is positive. So this is plus I squared k squared. I squared gets you negative k squared. Similar here, this is I k squared. This would be the same as I squared k squared, so that's negative 1 times k squared. So we can pull this negative k out, or sorry, the negative k squared out, and that would give us minus h bar squared 2m times negative k squared times a to the e I kx plus b e to the minus I kx. So this negative here and that negative there are going to cancel each other out. Right, so plus and plus. So essentially this is this part here is our psi, well, psi of x. All right, we got it back. This part here is E. So that is our energy. What this says is K can be any value. Right? We have no restrictions on K. So, energy for a particle moving freely is not quantized. There's nothing that forces the energy to be quantized for a freely moving particle.
Say that again, one more time. So there's not.
It's not quantized. Energy of a freely moving particle is not quantized.
Me.
Therefore, E is not quantized.
It can be any number.
Yep. Well, any positive number. Energy has to be positive. If you're looking at the total energy. Well, I guess it depends on how you're doing it. Yes, E can be any number. Now, if we take that particle, if we confine it to a box, we're going to find that the energy then becomes quantized through a derivation that we will be doing next time.
Wait, so E is not quantized. Isn't that like opposite of what quantum mechanics says? Yes. Didn't we say like if you quantize the energies, the math works out pretty well?
Mhm.
This is E is not quantized.
So the systems that we had been looking at were where the particle you're talking about is restricted to a location.
Unless
Right?
you-
Once it
yeah.
flies off, it can have any energy.
So once you add constraints, it has to be quantized.
And that's what we're about to do. But we have 3 minutes. And this is not 3 minutes. Okay?
But is that for the homework?
Um,